Good afternoon, everyone. My name is Longtian, and next to me is Youze. We are presenting our work, single pass document scanning for question answering on behalf of our team at UC San Diego. This is a joint work by Weili, Jianyou, Wang, Youze, Zheng, Longtian, Qirui, who is in the audience today, and advised by Dr. Taylor Berg-Kirkpatrick, Dr. Ramamohan Paturi, and Dr. Bergen. So answering questions about long documents has always been a challenging task for large language models, especially when understanding long-range dependencies within a document is needed to correctly answer the question. We give an example to answer this question. Where will Dr. Adams' keynote speech be held according to the updated schedule? An LM must accurately identify both sentence 10 and sentence 50, where sentence 10 says Adams' speech will be held in hall A, and later sentence 50 says all events in hall A will be relocated to room 210. This brings us to the core trade-off in long context QA today. On one hand, we could feed the entire document to a massive LM. This gives the model full context, but the cost is often prohibitive. On the other hand, we can use a standard RAG pipeline. We split the document into chunks, use an embedding model to find relevant pieces to a given query, and feed only those relevant pieces into the LM. This is efficient, but by breaking documents apart, we risk losing that crucial global context we just saw in the example. The embedding model might find hall A, but completely miss the update about room 210 because it lacks awareness of the document as a whole. This leads to our central research question, which is, can we have the best of both? Can we process the full context efficiently without losing global coherence? And the answer is yes. As you can see here, our method in the blue circle and orange square achieved better peak performance with better efficiency than the alternative method, taking into account the global context efficiently. For example, our 1.3 billion parameter model is more accurate than the 7 billion parameter NV embed model, while being over 6 times more efficient. This is the efficiency and accuracy we were aiming for. I'll pause for a few seconds here for you to take a look at the figure. Our approach is a simple two-stage process. First, given a question, instead of chunking, we use a small, highly efficient state-space model to do a single pass of the question, followed by the entire document. This scanner reads the text from beginning to the end in linear time, maintaining a memory of the entire preceding context. Second, we take the top-ranked sentences and feed them to a powerful generator model. We get the efficiency of a small model and the reasoning power of a larger LM. So let's look at the architecture. It's built on Mamba 2, a state-space model known for its linear time processing of long sequences. We prepend the question to a long document. After the model processes the document, a classification head is trained to predict whether a sentence is relevant to answer this question by producing a logit value, one sentence at a time, from the left to the right. At test time, sentences with the highest logits are selected. These top case sentences are then passed into the LM to generate an answer. To train this scanner, we use a standard binary cross-entropy loss. We train the model to predict which sentences are relevant to answering the given question. But this immediately raises an important concern. Where do we get the training data? Well, there are many open source long documents from financial reports, legal contracts, books, and scientific papers. There's no existing training dataset with long documents and sentence label relevance labels for QA, so we had to create our own. Our goal is to create data points that are triples of question, document, and relevant sentences.
So our first attempt was a simple and local strategy. We would first take a random chunk from a document and prompt GPT-4o Mini to generate a question that could be answered from the chunk alone. So this may have the same limitation as RAG, as it only teaches the model to find locally relevant information. And therefore, we tried a link-based strategy. So instead of doing one chunk, we give GPT-4o Mini an initial chunk and a wider context window. We then ask it to find another chunk somewhere else in the document that has a meaningful and natural dependency linked to the first chunk. So this meaningful dependency could be a thematic development of a recurring character from a novel, or a causal link from a legal contract, or something else. Once this link dependency is found, we prompt the model again to generate a synthetic question that can only be answered using information from both chunks. So this process gives us training examples that force the scanner to use long-distance information. And we apply this link-based strategy to a diverse corpus of raw documents drawn from publicly available data sources, including Project Gutenberg, government reports, financial documents, and legal contracts. We trained models on documents of length up to 10,000 tokens, and for all documents of length more than 10,000 tokens, we divided them into non-overlapping smaller subdocuments up to 10,000 tokens. And for evaluation, we tested our system on a suite of 41 public QA benchmarks, covering a wide range of document types, including educational, creative, official, and conversational. And the documents in our test set range from a few thousand tokens to over 700,000 tokens. And as you can see from the table here, the average document length is around 69,000 tokens. Our evaluation setup is pretty straightforward. So for the SP scanners, we select the top 50 sentences, which we fit to GPT-5 to generate the answer. For embedding models, we consider two setups. One is to select top 50 sentences, and the other is to select top 5 chunks, where each chunk has around 300 words. This is a standard RAG setting that used in previous papers. And empirically, we found retrieving 5 chunks yields better performance than retrieving 50 sentences across all embedding models, which could be because the chunk retrieval retrieves 25% more tokens than the sentence level retrieving. To be more than fair, throughout the paper, we reported performance from chunk retrieval setting for embedding models. And for our 1.3 billion parameter SP scanner, it achieves an average accuracy of 72.1% across 41 benchmarks. This is higher than competitive embedding models like NVEmbed v2, and it does so with far fewer flops. Our smaller 130 million parameter SP scanner outperforms all embedding models that have billions of parameters while being an order of magnitude more efficient. And if you look at the bottom, you see the computational cost of using a full context LLM, such as Gemma 3 and Llama 3.1, to generate the answer directly with a full context. And our methods provides a path to achieve high accuracy. And this graph shows as the document length increases, what would the accuracy change. The lighter line shows the embedding baselines. The solid blue and orange line shows our models. The dashed black line is the full context GPT-5 model. And SP scanner shows strong performance on documents up to 256,000 tokens, despite being trained on documents of length up to 10,000 tokens. So for very long documents, the models achieve the same accuracy as full context GPT-5 at a fraction of the cost. We also conducted the ablation to evaluate different synthetic data generation approaches. The link-based data generation approach, which forces the LLM to retrieve information from distant part of the document, performs better than the local strategy, in which case the questions can be answered based on local information within the document. And one may ask, does the improvement come from SSM? Is it just because state-space models are good? To test this, we compared our discriminative scanner to M2BERT, which is the SSM-based embedding model. Our 130 million parameter SP scanner achieves 71.2% accuracy, which is much higher than M2BERT. And this shows that the improvement doesn't just come from using an SSM model. And finally, we wanted to ensure that our retriever strength wasn't just tied to one specific generator. We tested it with a range of models, like from Llama 3.1 to Gemma 3 to OpenAI's GPT-4o and GPT-5. And as you can see, across the board, the SP scanner models consistently enable the best performance, regardless of the generator, and this demonstrates the fundamental strength of our approach. And to summarize, our single-pass document scanning approach preserves global context at linear cost, and our SP scanner models are small, with size 130 million parameters and 1.3 billion parameters. Our approach also beats embedding models across 41 long document tasks, and despite being trained on documents up to 10,000 tokens, our SP scanner could generalize to very long inputs way beyond its training documents. We also show that our SP scanners could work with different generators, so it can be readily served as a plugin module for different generators. And also, as you probably have observed, our current SP scanner processes the documents from left to right, which is a unidirectional approach. A natural next step is to train with a bidirectional state-space model to overcome its limitation. And also another point of possible improvement comes from a better synthetic data generation approach. So right now, our link-based approach only identifies 2 chunks. With the LLMs and more sophisticated pipelines, we could potentially extend to identify 3 or even more chunks that share real and natural dependencies with each other, and also generating high-quality queries. Lastly, we want to mention that there are certain long-context QA tasks that ask the model to summarize the document or perform the counting task. So this kind of task may not be suitable to use our SB scanner to perform. And before we proceed to the QA, we want to sincerely thank you all for listening to our talk. And for information, Longtian, Qirui, and I are applying for PhD programs this fall. So thank you for listening. And our poster is right after this at number 32. Thank you.
We have time for maybe 1 or 2 questions.
Hey, thank you for the great talk. I have 2 quick questions. The first one is, like in general, what's the latency of the scanning process compared to just prompting? You put the entire documents in the context. And the second question is, did you do any re-ranking during the scanning process?
So the first question, like we also compared the teraflops, so the computations compared with the full context like Gemma models and Llama 3.1 models. So if you see the teraflops, like we're much more efficient. But we obviously like we don't count the later stage of GPT-5 generation. But we all just like feed 50 sentences to the generator, so it should be much more efficient. And for your second question, sorry, what's your second question?
So the second question is, did you use the scanner model for re-ranking the documents?
So we prepend the query to the long document and process the document once, and we just retrieved the top 50 logit values, so we didn't do any re-ranking.
Okay, thank you.
Yeah.
Yeah, it is very interesting work. I just have a quick question. So, like SSMs are feed forward, which means that you can forget the query for a very long document when you come to the end. You could potentially forget the query. So have you looked at whether you should like maybe always pay attention to the query while still keeping the linear scaling? Does the question make sense?
So during our training process, we tried approaches of putting queries at the end of the document and also trying to put queries along with the sentences. The results show that the change in the training data this way should not change or tamper with our results much. We're not exactly sure why that happens, but that's like our findings from the trainings. Yeah.
Thanks.
All right, thank you. That gets us to the end of this session. Let's thank the speakers, and we have a poster session on the 7th floor.